In this video, I want to talk about the details involved in calculating probability, as well as the different types of probability. So let's begin with theoretical probability. And this is based on the assumption that all outcomes are equally likely. One of the things involved in calculating this type of probability is counting the outcomes. So we have at least 3 different ways to do this. So for example, let's say we are tossing 3 coins, and we want to list all of the possible outcomes, right? Or even count how many there are. So the first option for doing this would be listing, and you would just go through and let's assume each coin can be a head or a tail. So you might start with all heads, and then move into 2 heads and 1 tail. Okay, and then order matters. One reason or explanation for this is that the coins are not necessarily all the same. So if you have a quarter, a dime, and a nickel, then a tails on the nickel is different than a tails on the dime. And you would just keep going, and you would consider different arrangements, and then different numbers of heads and different numbers of tails. All right, so one disadvantage to this method is that you may miss an outcome if you don't have a really clear organization system. And then if there are a large number of outcomes, it just might be kind of inconvenient to list all of the outcomes if you're more just concerned with how many there are. A slight improvement on this would be to use something called a tree diagram to do the listing. And this is just one organization method that kind of helps keep track of things. Right? So what we would do is consider the act of picking a coin or flipping a coin as a process, and then we would list out the different options for each of the 3 processes, picking the 3 coins. Right? So the first coin, when that one's flipped, it can be either heads or tails. Okay, and then if we're flipping 3 coins, we would already have one of these results on the table as we move into the second coin. All right, so we'd use branches to show that we're moving on to the next process. So if the first coin is heads, the second coin can either be heads or tails. Right, so it's independent of the first coin. The first coin doesn't affect what the second coin could be. Typically now you'll keep some sort of an order convention. So because I did heads and then tails, when I move on to the next process, I also do heads and tails in that order, not tails then heads. And this just helps keep track of all the different options. Okay, if the first coin is tails, the second one can be heads or tails. And then moving on to the third process, that third coin can be heads or tails in any of these cases. All right, so before we get to that point, we have 4 cases right now. We've flipped 2 coins, and we have seen before that there are 4 outcomes. It could either be heads, 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 tails, tails, heads, or tails, tails. There are the 4 outcomes. All right, and then moving on from each of those 4, the third coin could be heads or tails. So now we end up with an organized list. Right, it's following a nice uniform symmetric structure, and then you just count the ends of the branches to see how many total outcomes you have, and we can see that there are 8. Now if you want an improvement on this, we have the multiplication principle, and while this doesn't list all of the different options, it is a very fast way to count how many outcomes there are. Right, so we would count the number of outcomes for each of these processes. So the process is the thing we're doing. You can think of that as flipping a coin, drawing a card, choosing a child from a family, anything like that. Right, so we have 3 processes. So picking the first coin, there are 2 outcomes, heads or tails. Then for the second coin or the second process, 2 options, and the third coin also 2 options. So if you multiply those, the multiplication principle tells us that that's going to be the total number of outcomes for this experiment overall, the act of flipping all 3 coins. Now this will work in any situation where the processes are independent of each other, right? So, if flipping the second coin depended on, if the outcome depended on what the first coin was, then things get a little bit different. But in these situations so far, that's a handy principle. Now you can generalize from there. So, for example, if we were flipping maybe 6 coins, all right, or actually, let's do, I want to switch this. No, we're good. We can do 6. Okay, so if you're flipping 6 coins, then there are 2 options for the first process, or flipping the first coin, 2 options for the second coin, and so forth. And then same principle, you can just multiply and get the total number of outcomes. Right? Or you can do 2 to the 6th as well as a shortcut. Sometimes people get confused as to whether this is 2 times itself 6 times, or is it 6 times 6, or is it 2 times 6? I've seen all of those answers. All right, so you want to keep in mind that each thing you're multiplying represents a different process. All right, so when I see this 6 times 6, this would mean that I'm doing 2 things because I'm multiplying 2 numbers. All right, so this would mean I'm doing some sort of a process with 6 outcomes, and then doing another process with 6 outcomes. So this would be more appropriate for like for rolling 2 dice, and then you've got 6 outcomes on each die. 2 times 6, this would be doing 2 things where you have 2 outcomes for the first thing and 6 outcomes for the next thing. So this would be maybe if you're tossing a coin and then rolling a die and then seeing how many different combinations of outcomes there are. All right, let's talk about the probability of an event not occurring. There is a formula for this, and the purpose is mostly just to use this as a shortcut. Right? So if you already know the probability that an event occurs, then it's very fast to find the probability that it does not. Right? So this is based on the fact that we only have 2 options for an event. Either it happens or it doesn't happen. So together, those 2 probabilities would equal 1, meaning it's absolutely certain that either the thing will happen or the thing will not happen. All right? So let's consider an example. And then one more formula, so we can just sort of rearrange this. If you subtract the probability that the event occurs for both sides, then you end up with the fact that the probability that it doesn't occur is 1 minus the probability that it does. Okay, so as an example, let's say that you have a small bag of M&Ms and you count them up, there are 62 total, and they come in red, orange, yellow, green, and brown in the bag, and we can count and record these frequencies. All right, so let's say you want to find the probability that the M&M is not yellow. All right, so one option for doing that would be to count up all of the non-yellow M&Ms, and that would involve adding 15, 12, 11, and 16. All right, so you'd have to do an addition first, right? Or shortcut is to start with 1 and subtract away the probability that an M&M is yellow. All right, so now you're doing 1 minus, and then the probability that it is yellow would be 8 out of 62. So you can see in this case we saved just a small amount of addition, but let's say you were dealing with maybe a survey with a lot of different options. Maybe it's like people's favorite ice cream flavors or something like that. And if you had a list of 20 or 30 different flavors, you might actually have to add up 20 odd things in order to find this probability versus just doing a single subtraction. All right, so the longer this list of options is, the more of a shortcut this turns out to be. All right, and then to just subtract, remember that you can use common denominators. So we would make 1 into 62 over 62, and then subtract 8 out of 62. So that probability would be 54 out of 62, and then you would reduce that to lowest terms or a decimal. This is an example of a probability distribution that was in your reading. This one is for the sum of 2 dice, and you can show probability distributions as tables like this or as histograms. This one just gives a list of all the different events or sums, and then the probability of each of those things. Right? So it's good to know this, or to at least have seen this, because the probability of getting a sum is not the same as the probability of getting a single number on one die, right? So if you were to think that there's only one chance of getting a 7, that's quite a bit off, because there are multiple ways to get the number 7. An application of this is in board games, anytime where there's an advantage in getting certain sums. One that comes to mind is the game Settlers of Catan. And if you've played this before, you've seen these little number chips that go on all of the squares. And there's an advantage to having your settlement along one of these hexes with these numbers, right? And if you roll that sum, then you get stuff in this game. So you would want to be along numbers that are rolled more frequently in order to be able to get more things. All right, so these represent the sums, and you can see they start at 2 and then go all the way up to 12. Okay, all possible sums. And the numbers 2 and 12 only occur once in this game, and then all of the other tokens occur twice, and those are more likely. The little dots below each number actually do indicate exactly these probabilities, just without the 36. So you could think of it as, I guess the frequency out of 36 possible options. Okay, so for example, the 2 has 1 dot because there's only one way to roll a sum of 2. You'd have to roll 2 ones. Okay, whereas something like 6, it has 5 dots below it, and that's because its probability is 5 out of 36. There are 5 ways to get a sum of 6. Okay, let's look at the formula for odds. And one thing I wanted to do is an example of how we can work backwards from this formula for odds to calculate probability. Okay, so let's say, so odds for an event compares the probability of that event happening to the probability that it does not happen. All right, so for example, let's say we'll use a classic example. In a bag of marbles, there are 5 blue and 6 red. Actually, let's do, no, that's fine. Okay. All right, so then the odds for getting red would be the probability of getting red, so that would be 6 out of 11, okay, divided by, or compared to, the probability of not getting red, which should be 5 out of 11. Okay, and then we would commonly express this as just 6 out of 5. Okay, so you can either just really informally think of getting rid of the 11s since they're the same in numerator and denominator. You could think of multiplying this entire fraction by 11 over 11, and that would cancel out the 11s, and that's allowed because 11 over 11 is just 1, right? Or you could go through the process of dividing by a fraction. So this would be 6/11 times 11 over 5. Then the 11s cancel, cross cancel, and you're left with 6/5. All right, so we know how to calculate odds if we have the total frequencies and probabilities to begin with. But let's see what happens if we don't have that. Let's see if all we know is the odds. Can we work backwards from there? So let's say we know that the odds for a green marble, okay, are 5 to 8. Okay, and then let's see if we can find the probability of getting a green marble. All right, so notice now we don't know the total. We know that there are 5 out of some number of ways to get green. Okay, but we don't know what it's out of. Well, you can find this just by adding the 5 and the 8. Okay, so this means there are 5 ways to get green and 8 ways to not get green. And we don't really care if the 8 represents red or blue or both. It's just important that it's all of the other options that are not green. All right, so add 5 and 8, and then the probability of green would be 5 out of 13. Probability of not green would be 8 out of 13, all of the other options. The last thing I want to talk about is differences between the three approaches to finding probability. And what's interesting about this is that the first two here don't actually really give us great definitions of probability. And I find it interesting in your textbook reading, subjective probability is barely touched on, but actually probability focuses more on subjective probability at this point in time because we've acknowledged that these first two definitions are incomplete. All right, so the issue with the first definition is that it assumes a definition of probability even as it tries to define probability. Okay, so what it says is that theoretical probability is based on the assumption that all outcomes are equally likely. Okay, well, what does it mean for something to be equally likely? We mean that it's equally possible or equally probable. So it's used the word probable in this definition. All right, so this isn't really a good definition of probability. It's more of a handy rule or a formula for calculating probability. It tells us how to make this fraction, but it doesn't really consistently give us an explanation of what probability is. The issue with the second type of probability, the relative frequency one, is that it is based on past observations and experiments. And what's missing from this is the fact that these can vary. So you may have seen this if you've flipped coins. You don't usually get exactly 50% heads and 50% tails. It's usually a bit off. And so theoretically, there's some true number, that 50% probability that we're sort of aiming for, and we're hoping that those frequencies get close to. So if we were to repeat these experiments or trials an infinite number of times, theoretically we would get exactly 50% heads and 50% tails. Okay, but in the meantime, until we get to an infinite number of observations, we're really basing this probability on what's happened in the past. And there's no guarantee that that's what's going to happen in the future. You can see this with weather. We can predict what happens with the climate in any region based on what's happened in the past. But if there are other factors at play or reasons why the past climate wouldn't happen in the future, then that relative frequency type of probability isn't the best descriptor of what will actually happen. Subjective probability, it is an estimate based on experience or intuition, but I feel like that makes it sound weaker than it actually is. This type of probability is perhaps a better philosophical explanation of what probability is, and it's acknowledging the fact that we are just trying to approximate or estimate or predict, and that we do not know for certain what these probabilities are. So I think when you're looking at flipping a coin or rolling a die, it's really easy to think, oh, it's exactly 1 out of 2, exactly 1 out of 6 for each of those outcomes. And it sounds almost so certain that we kind of miss the fact that we're just describing things that are possible or probable and not certain at all. So if you're interested in subjective probability, this is the direction that modern probability has moved in. And what it does is it considers, we could say, a priori experiences and things that we know, and it takes into account all of the complexities involved in making one of these estimations. So for example, if you're predicting whether or not somebody will get diabetes, right? If you just do it as a relative frequency, like how many cases of diabetes have been observed in the population, that's perhaps not as accurate as taking into account the person's family medical history. So while we are basing this type of probability on experience and intuition, it's not uninformed. Some of these things do affect probabilities, and we want to take into account as many of these factors as possible. So if this interests you, you can look up what's called Bayes' theorem, and this deals with conditional probabilities, and that would give you a good place to start. And then the book that I've referenced several times before in this course, How Not to Be Wrong, has a chapter on this and how this applies to statistics as well. All right, so take a look if you're interested, And I think that's a good start for the fundamentals of probability.